Welcome to the summer pre-calculus course, and I want to go ahead and right away and apologize for the poor quality of my handwriting on this, which hopefully will improve as the summer goes on, although I have had a lot of practice at this already, which is the scary part. But it's difficult anyways to write on a tablet, but I'll do my best to make this writing legible for you guys. But anyways, here's the first day of summer pre-calculus. This is 6/16. And we're going to try and, over the course of the summer here, to fit in a full pre-calculus course, which I'm going to go ahead and say right away, that's a lot of material. We're going to do our best to get through it, and we'll hopefully get through all of it, but know that it is a lot of material. I'd say pre-calculus, of all the courses, is a very dense class in terms of material. Very dense material. There's a lot of material to cover. For those of you who haven't taken pre-calculus, which is everyone except for Caroline here, just so you know what pre-calculus is, really a better word for pre-calculus could be Algebra 3, or a better title for pre-calculus could just be Algebra 3. It's just an extension of the things that you already learned in Algebra 2. We're going to add some additional topics, and most of what we're going to do, though, is we're just going to expound upon topics that you've already covered, so types of functions that you're familiar with. We're going to come up with some more universal rules for functions that are going to apply to all different function families that will sort of unite all these different sort of what seemed like maybe disparate, meaning different topics in Algebra 2. And that's really what you need, this more sort of holistic knowledge of all these different algebraic topics going into calculus. You need to have that all sort of down. So this is one last extension of algebra, essentially. You've taken Algebra 1 and Algebra 2. This is really Algebra 3. And once you're done with this, you'll have the algebraic grounding that you'll need to be able to tackle calculus, hopefully. All right. So first thing I want to do, like I said, and let's see if I can remember how to make a new page here. All right, so the first thing I want to do really quickly is get a sense from you guys which Algebra 2 topics that you thought you maybe weren't quite totally comfortable with at the end of the year this year. So let's just go around. Just throw your hand up in the air. And are there any topics that you remember from the final that didn't really go that well for you? And even pre-cal, if there's stuff from pre-cal, you're like, wow, we definitely want to go over that again, that you want to focus on. Because it's going to help me know what you feel like you need to work on in addition to me sort of filling that out as we go through. So what do you guys think? Anything in particular that you can remember from the final when you're going through and you were just like, I don't really get this? I know it's been a while. Trig. Okay, let's put that in the list. Trig is always something that we always need more practice with trigonometry, so that's a good one for sure. And we will definitely cover trigonometry. And that's one of those subjects where I was just talking about, you've seen trig in geometry, really basic trig. You saw trig last year in Algebra 2, more of an extension of trig to angles beyond 90 degrees and some of the trigonometric rules like law of sines, law of cosines. And we're going to, talk a little bit more about those, and then we're going to add things like the trigonometric identities, and we're just going to go into more depth with trig. Caroline remembers the identities. That's probably one of the parts that you didn't maybe have so much fun with. Yeah. We'll talk about some more advanced trigonometric equations that we want to solve, because ultimately for calculus we want to be able to solve a lot of different types of equations, and trigonometric ones are one of the most important ones. So trig, anything else, you guys? Quadratics, exponential, logarithmic functions, any issues there? Was it the last thing? Was the last thing you guys did exponential and trigonometric? We were in a little bit different.
I think so.
I think so, yeah.
I had that stuff the last month. You didn't put in the final. It was like what was it? I don't remember what it was. It was.
Oh yeah, rational. Yeah, rational expressions. We're going to go back and we're going to talk about rational functions, which we don't cover at all in Algebra 2. And in the process of doing that, we're going to recover all that rational expression stuff, and we deal with fractional algebraic equations and expressions. So trig, nothing else though? All right, that's fine. All right, so there we go. I'm an old pro now. What we're going to start off talking about today, let's just review some stuff, some basic stuff first, which are going to be our basic algebraic properties, both exponential and just number properties. Really, we're not going to like go through this in detail. I'm just going to give you the properties, and then I'll throw some examples up that involve those properties that I'm going to have you work on. So basic properties that you're going to need to know, of course, the distributive property is one of the really important ones that you're probably very familiar with at this point, which just says that if I have A times B plus C, I can distribute it through and get AB plus AC. You've known that since Algebra 1, but it's worth just making a note of that really quickly. And what's important about the distributive property is that you can go in both directions, right? I can distribute the A through the B and the C, right, and go from left to right here, as I'm seeing right now. So start here and move from left to right. But I can also go in reverse. I can say, well, if I have an expression that looks more like this one, the AB plus the AC, I can go in reverse. And what do we call that process when I'm doing distribution in reverse? It's a type of what? Starts with an F. Factoring, yes. So we can use the distributive property and any property that involves an equal sign, right? Because equal signs obey what we call the symmetric property. We can use them in any direction, either from left to right or from right to left. And what do we usually refer to the process of using the distributive property, in the opposite direction, going left to right? What do we call that? Distribution is a type of, it is distribution, yes, but what is it a type of? A bigger umbrella term that encompasses more than just distribution. What's the opposite of factoring? When we unfactor something. Starts with an S. Simplifying, yes. So we can almost think of simplifying and factoring as sort of like inverse processes, right? One is the reverse of the other. So the distributive property is sort of the basis for a lot of the factoring that we do. That's the first one. The other ones that we need to know through and through are your exponent rules, which are properties for exponents, of course. These are the ones that people tend to still have issues with. Let's just go through them, make sure we have them all down. And in a second here, I'm going to give you some examples to work through, just so we know that we have it for sure. So exponent rules, right? The first one is what happens when I take something like a to the n times a to the m. What do I do in this case with my exponents? Yeah, I'm going to add them up. So a to the n plus m. What do I do when I divide exponential expressions? And it's important that they have the same base, right? And the base is the part, let's see, I didn't really leave myself much room, but the base is what a is, right? The base is the number that we're raising to the power. So if the base is the same, these rules apply. But let's say the base wasn't the same, it was like x and y, we couldn't apply these rules, right? That's a really important property. So when I divide, what do I do with my exponents? I subtract. Whoops, let's not make that red. Just erase that, I guess. So yeah, we subtract, we get a to the n minus m. If I ended up with like a negative number, what if I had like a to the negative n? Like if I subtracted n minus m and I ended with a negative number, how can I write a negative exponent, or how can I make an expression that involves a negative exponent only have positive exponents? That's 1 over a to the n, exactly. And if I had 1 over a to the negative n, how could I write that without any negative exponents? Just a to the n, yeah. And last but not least, if I have a to the n, and that whole thing is raised to the nth power, if I raise a power to a power, what do I do with my exponents? Multiply, all right. There are more exponent rules, but those are the major ones that we need to pretty much know cold at this point. And these rules we know apply whether our exponents are whole numbers or whether they're fractions, right? We can apply these rules the same exact way if we have fractional exponents, which of course we can, and I should add this as well, the last exponent rule. That we also have fractional exponents, so if I have a to the, let's say, n over m, that's a fractional or rational exponential expression. How can I express that as a root instead of an exponent? Yep, the mth root of a to the n, exactly. Which doesn't matter whether the n is on the inside or whether it's on the outside, right? Whoops, that should be an n. That's one of the problems I'm going to have, is that my m's and n's look a lot like each other, unfortunately, and even more so when faced with the challenge of this whiteboard. So that's important to know as well, being able to convert from exponential to what we call radical form. So we would call this the radical form of the equation. All right. Okay, so let's look at some basic examples, and then we'll move on to the next topic after that. So let's do it right here. So for example, the types of things that we'd like to be able to do with these rules is, first of all, if I give you the expression, let's say 3x squared y minus 9x cubed y to the 8th. I would like you to go ahead and factor that using the distributive property in reverse. I'm pretty sure you guys have the distributive property down in the other direction, but let's make sure that we have our factoring using the distributive property covered. And let's also go and look at an example where we have some weird exponents going on. And by weird, I mean fractional and or negative. So let's say we have this. So 3 to the, say x to the negative 2 times y to the 5/3 all over. And I'm going to take this whole thing, I'm going to square it. And on the bottom here we'll have 9x cubed y to the 1/6. Well, it'll be y to the negative 1/6. So for this second one, I want you to just fully simplify that exponential expression. And I want you to make all of the exponents positive in the process. So fully simplify it and make sure that you end up with all positive exponents. Okay? So these are two examples that will have you use pretty much all, with the exception of that last property about converting from radical to exponential form. It'll have you use all those different exponent properties at once here. All right, so give that a shot, and as soon as you're done, let me know. And so I'm going to make sure I just fix this one right there. So that looks, whoops. Nope. Undo that. This one right here, that's x to the third. For the first one, 3x squared y minus 9x cubed y to the 8th. If we're factoring using the distributive property, we should first identify what the GCF is, right? And that's what we're going to be factoring out. What is my GCF in this case? The greatest common factor of the two terms.
3x squared y.
Yep, 3x squared y. So that's what's going to end up coming out. And what's that going to leave us with on the inside here? If I take out the 3x squared y from there, I'm just going to be left with what? 1. Common mistake there is some people end up with 0. Remember, when we divide and everything goes away, it's not because it's becoming 0, it's because it's becoming 1. And then 9 divided by 3 is 3x cubed divided by x squared is x, and y to the 8th divided by y is y to the 7th. Right, so that's an example of us using the distributive property in reverse. Now, we're probably going to do this in this next one in a multi-step process here. I would probably start off by applying that square on the outside of the parentheses first, and then I'll handle the negative exponents afterwards. So when I take this whole expression right here to the second power, what am I going to end up with? What's 3 squared? 9. What about x to the negative 2 squared?
X to the negative 4.
Yep. And then y to the 5/3 squared?
Y to the 10/3.
10. I'm taking 5/3 and I'm multiplying it. Oh, I'm sorry. You're right. Never mind. So 10/3 all over. Same thing. 9x cubed. Y to the negative 1/6. So one thing we can do initially that I'm sure you're seeing right away is we can do some cross simplification and cancel the 9s. What should we do with my negative exponents now? Hopefully I have room to fit this down here. What should I do with my negative exponents? Because we want to make them positive. That's what's one of our goals here. What'd you do?
I took the 3, wait, no. I took for the y, I added 1/6 to 10/3.
Yeah, so you brought the 1/6 to the top, right, to make it positive?
Yeah.
So I'm going to do this in 2 steps, just so the people who are following along on the internet here can see. So I'm going to bring the y to the 1/6 up to the top first, and then I'll bring to the x to the negative 1/4 down. Or sorry, x to the negative 4th, I should say, down.
Yeah.
And then you're combining by adding, which you absolutely should do. That's perfect. So 10/3, how do I add 10/3 and 1/6? Common denominator? How many sixths is 10/3? 20/3. So it's 20/3 plus 26 plus 1/6 will give me y to the 21 over 6 over x to the 7th. And that's fully simplified now. No negative exponents. So, knowing how to handle our negative exponents is really important, particularly when we get into exponential functions. So, that's good stuff right there. All right, basic properties of real numbers. Today, another topic of review that you should be equally as familiar with, we're going to discuss will be lines and linear equations. All right. Lines and linear equations. So, to talk about lines and linear equations in a second here, we need to talk about the Cartesian coordinate plane. Right? So the Cartesian coordinate plane is just 2 number lines put at a right angle to each other, right? The horizontal one is the x-axis, the vertical one is the y-axis. All right, and getting back to geometry here, going all the way back to geometry, if I have 2 points, any 2 points can be joined by a line, right? And a line segment runs between the 2 points. A line is something that goes on forever that might go through those 2 points, but has an infinite length, essentially, whereas a line segment has a very fixed length. And so to describe any 2 points on the Cartesian coordinate plane, we use Cartesian coordinates. And so let's say this is the point x1, y1. And over here, this is the point x2, y2. Right? And so the x and the y coordinates give us a horizontal and vertical location that allows us to pin down any point on the Cartesian coordinate plane. And if we know the points that this line passes through, it's going to tell us really important information about the line itself. But before we even get into talking about the actual equation of lines, let's talk about how we can relate points to each other. So if I have 2 points on the coordinate plane, what are some interesting facts that relate those 2 points to each other? Like, for instance, if I wanted to know how far are those points apart from each other? I don't even remember, how do I find the distance between 2 points on
Distance.
the distance memorized at one point? Right? Anyone remember what the distance formula is? If I have those 2 points,
Square root, something like that.
definitely involves a square root. So let's say d is equal to the square root of, I'm going to outline it for you here. Can anyone fill in the blanks here?
y2 minus y1 plus x1 plus x2 is the opposite. I don't know.
Whoops. Yeah, I put y2. It should be y2 minus y1. x2 minus x1. What's the last thing I'm missing? Squares, yeah. Now, the whole reason for this, it stems from Pythagorean theorem, right? If I have 2 points here on the plane, here's the distance between those 2 points, right? The difference in x coordinates, if this is, let's say, x1, y1, and this is x2, y2, right? Then let's say this side of the triangle is the distance, right? That side is the distance between the 2 points, right? The other 2 sides of this is a right triangle. The right side here, I guess, or the vertical side, is going to be the distance between those 2 points. The y distance between those 2 points, I should say, y2 minus y1, right? And the horizontal side is going to be x2 minus x1 in length. And then if we plug all that into Pythagorean theorem and solve for d, we get the distance formula. So it's not hard to see where it comes from, in addition to knowing what it is and how to use it, of course. So we have distance formula. That's going to be important. Okay. What if I had the points x1, y1, and the points x2, y2? And what if I wanted to find the point that was halfway directly between the 2 points? First of all, what would we call that point? That's a special name. The what?
Midpoint?
The midpoint, yep. And how would I find the midpoint? What do you think is going to be true about the x and the y coordinates of our midpoint? And this one's one you can sort of just think through sort of conceptually. What do you think is going to be true about the x and the y coordinates of our midpoint? If the point is halfway between the 2 other points, then what do we think about do you think the x and the y coordinates might be halfway between,
Yes.
which means that they would essentially be the average of, right, the x and the y coordinates of the points we're talking about. So the midpoint is going to be x1 plus x2 over 2, the average, or halfway between x1 and x2, right? And the other one's going to be y1 plus y2 over 2, right? So that you can sort of think of in a conceptual way. Okay. All right. So I'm going to give you a couple questions to work on that are going to involve midpoint distance formula, and hopefully that these ones will hopefully get you thinking a little more critically about these concepts. First of all, basic question. What is the distance between, let's say the point -2, 3, and -5, -8, right? And this will be interesting because we'll be able to talk about reducing radicals as well. But anyways, what is the difference between those 2 points? First question. Second question is, if the point 2, 3 is the midpoint between, let's say, 5, 6, and the point A, B, what is A and B? Okay. So we're not going to be, we're going to want to use the midpoint formula for the second question, but we're not going to be applying it directly necessarily. Okay. So take a crack at those 2 questions. We'll give you 5 or 10 minutes. Let's take a look at this distance formula one first. So the distance. Now, when I'm using my distance formula here, does it matter which point I call point 1 and which one I call point 2, or is it all going to come out in the wash regardless? Does it, right? So I can either call -2, 3, point 1, or I can call it point 2, and the same is true for -5, -8. The key is once you've picked a point to be either point 1 or point 2, as far as how you're plugging it into the formula, you have to be consistent, right? So what that means is, let's say that this is point 1 and this is point 2, right? When I'm plugging into my formula here, I'm just going to sort of write out the framework of the formula here. When I'm plugging into the formula here, that means that if -2 is going to be my x1, right, and -5 is going to be my x2, then I'll put -5 minus -2 in here, right? -5 minus -2, right? And over here, I'll put -8. That's my -8 is going to be my y2, right? And my y1 is going to be 3. So -8 minus 3. Notice I was very careful right here to put minus -2. Most common mistake when using distance formula is a sign error of some sort. When you have subtraction and you're subtracting a negative number, that's always going to become addition, right? So be really careful. I always like to put it in parentheses like this just so I don't forget, because even I forget every now and then. So -5 plus 2 will give me -3, right? This will end up being -3, and when I square -3, I'm going to get 9, right? Over here, -8 minus 3 is going to be -11, right? And what's -11 squared? 121. So we're going to get the square root of 120. That's my distance between my 2 points. Now, really quick review with radicals here. Do I want to leave that as square root of 120, or do I want to do something with it? Simplify it, if you will. Do I want to simplify it? Can it be simplified?
Yes.
How can I simplify it? What's a basic, and I'm going to put this up in the upper hand corner, what's a basic property of radicals here? If I have the square root of a times b, that's the same as this, as what? How can I break that apart by the multiplication going on? Times square root of b, yep. And that means if a or b is a perfect square, the square root of a perfect square, we know what that is, right? Which means if I can factor out a perfect square, there's that term, that factoring term again. If I can factor out a perfect square from the 120, ideally the biggest perfect square that is a factor of 120, then I can use this property right here to reduce it. So, what's a perfect square factor of 120?
I think you used 130.
Yeah.
So 120 is.
Oh, you're right. Thank you for fixing that. Whoops. Basic arithmetic is an important part of doing mathematics. Now the big question is, can I actually... Nope. So, I'm going to use a little trick that I've done in the past, which is going to make this really big. And I'm going to make it white. And so this is sort of the, I like to call this the ghetto eraser. It's not really an eraser, but it already locked the other part up. So, now that that's gone, we can go back and rewrite it as what it actually should be, which is square root of 130. Now, 130 is 75 times 2, which is 25 times 3. So what do you think is a, nope, sorry, 65 times 2, which is 5 times 13, right? So we have 2 times 5 times 13. So 2 times, wow, that I think I can't erase. Like I said, it's going to take some work. So the prime factorization of 130 is 2 times 5 times 13. So we see we don't have any perfect square factors. And so if we did, we'd break it apart and pull it out, but we don't, so we're just going to leave it as square root of 130. But just a reminder that if you do get a square root as a solution to an equation, make sure that you always do reduce it. Pull out any perfect square factors that you might have there. Okay. So that's the distance one. Now let's go to the next one here. To just sort of abbreviate it. 2, 3 is my midpoint. And my points that it is the midpoint of are 5, 6, and AB. Now, how do I set this one up here?
5 plus a over 2 equals 2.
Yep, so we're going to break it apart by exactly there. The x component and the y component. We're going to deal with them separately. So 5 plus a, we know by the midpoint formula that 5 plus a over 2 has to be the x coordinate of the midpoint, which we know is 2. Right? And the other formula we're going to set up is what?
6 plus b over 2 equals 3.
Exactly. 6 plus b over 2 is equal to 3. So this is going to actually segue nicely into one of the other topics we're going to address today, which is just solving basic linear equations, particularly those that have fractional amounts. If I have a fraction in a linear equation, how can I eliminate that fraction immediately? What's a good, really easy way to do that? Like, for instance, what I'm talking about here is this 2 right here. What should I do to this whole equation?
Multiply both sides.
Yeah, multiply the whole thing by 2, and that's going to get rid of the 2 in the bottom right there, right? So we'll be left with 5 plus a equals what? 4. Yeah, we got to make sure that both sides get multiplied by the 2, which means we will have a 4 over there. So a equals -1, right? And on the other side, we're going to do the same thing. Multiply the whole thing by 2. We'll get 6 plus b equals 6. So b is going to equal 0. And so that means the other endpoint the point that is AB is going to be the point negative 1, 6. So if 2, 3 is the midpoint and 5, 6 is one of the endpoints, the other endpoint must be negative 1, 6. There's another way to phrase that problem. Find the endpoint if you know the midpoint and one of the other endpoints. Okay. So basic distance, midpoint formulas, those are going to be important. Now, let's go ahead, and the next thing I would like to, if we're talking about lines, we can talk about lines in terms of what points they pass through, but we would like to actually be able to write functions that are equations of those lines, right? And so let's go through, if I have a line here, let's say the line, I go ahead and I'm going to universalize this. So there's a line in my coordinate plane, right? And let's say that the place that it crosses the y-axis here is going to be the point, well, what is the x-coordinate of any point on the y-axis, first of all? 0. So it's going to be the point 0, and I'm just going to call the y-intercept b. So the y-coordinate is going to be b. Let's say this line also passes through the points x1, y1, right? It passes through the point x1, y1. And let's also say that it has a slope of, oh, and by the way, slope. Probably talk about that really quickly. Slope is a way of measuring how steep a line is, right? And so how do we measure slope? What is the formula that is often associated with slope that we know? And describe it to me in any way you want. There's a bunch of different ways to describe it. Just give me any one of those ways is fine. Rise over run, right? How much does it go up versus how much does it go out? That's a ratio, and that just gives us a general sense of how steep the line is. If the number on top is really big, that would mean that it's going up way more than it's going over. That'd be a really steep line, right? And so it could correspond to a really big number. If it's going down, on the other hand, then the rise can actually be negative, and we have a negative slope as it goes down from left to right. And the bigger that negative number is, the steeper it going down, the bigger the negative number is going to be, right? And so, once again, it's just a good way of measuring steepness. It's the basic geometric idea behind it. And how can I quantify that if I know, let's say, 2 points that the line passes through? What's the rise going to be? Yeah, it's going to be the difference in the y-coordinates, right? So once again, this same general idea I had before when I was using Pythagorean theorem. If I have the point x1, y1, gosh, that's so bad. Okay, the point x1, y1, slightly better, and the point x2, y2, and I want to talk about the slope between them, right? The rise and the run are represented by the legs of this right triangle, right? So we have what we're going to call here the change in the y-coordinates, delta y, change in the x-coordinates, delta x, and delta y over delta x is another way to talk about it, which, as you said, delta y is just the change in the y-coordinates, y2 minus y1, and delta x is the change in the x-coordinates, x2 minus x1. So there's my slope formula. Okay. Now, if I want to talk about the equation of a line, so I want essentially a formula that if I plug in the x-coordinate of any point along that line, it's going to spit out the y-coordinate, which would be a function, right? A function, and let's just talk about what a function is really quickly. Relates to sets. In the case of the function of a line, the sets that we're talking about is the x-coordinate and the y-coordinate, right? So the equation of the line right, is a function that gives the y-coordinate for every x-coordinate along that line. And so there's a bunch of different ways to find the equation of a line based on different information that you might be given. So for instance, I'll click on the next page. Draw that diagram I had just a second ago. My line that goes through the point 0b, right? And it also goes through the point x1, y1. And my line's also going to have a slope of m. M is a variable letter often associated with the slope. Okay, so the equation line that you're probably most familiar with is slope-intercept, right? Probably the first one you might have been introduced to. Anyone remember what slope-intercept form of the line looks like? If I know the slope and the y-intercept of the line, what form of the equation can I plug directly into? Yep, y equals mx plus b. So that's where the b comes into play here, right? That's the y-coordinate of the y-intercept. And in the slope-intercept form, it goes right there. And the m is the slope of the line, right? The rise over the run, and that goes right there. And so if we know the slope and the y-intercept, it's very convenient just to plug into slope-intercept form. Unfortunately, a lot of times we don't know the y-intercept. We usually know the slope, but not always. Or we can at least find the slope. The other one that you might be familiar with is what if I just know a point that it passes through and I have the slope, which, as we're going to see in a second, is the same as just knowing 2 points that it passes through, because if I have 2 points, it defines a line, and therefore I must know the slope of the line. But let's say that I have the point and the slope that it passes through. What form of the equation would I then want to use? That would be very convenient for writing the equation of that line. Point slope. And what does that one look like? Yeah, I know, I sort of already gave you the name, didn't I? Leading question. Do we remember point slope form? If I know a point, and that point is going to be called x1, y1, and I know the slope.
Y minus y1 equals m times x minus x1.
Yep. Whoops. You were right, yes. So that's your point slope form. And so once again, if we know a point that the line... Did not mean to do that. I meant to go to my pointer. So if we know a point the line passes through, in this case x1, y1, we know the slope, we can plug directly into this formula. Very convenient in those instances. The last one that is not so convenient for writing the equations of the lines, but as we'll see later, is very convenient when we're solving systems of equations. It's called general form, and that's just the one that's ax plus by is equal to c. Right? We don't have to worry about that one so much right now, because the problem with general form, it's nice, like I said, when we're solving systems of equations, but the a, the b, and the c in general form correspond to literally none of the properties of the line. So it's not a very descriptive form. Whereas all of the parts of point slope and slope intercept form describe one of the properties of the line just by looking at it, which is convenient. The reason I'm erasing that is because with general form, generally you use capital letters for the a, the b, and the c. Not that it really matters that much, but to be precise. So, we're mostly going to use these first two formulas here when given information about the line if we want to actually write the equation for the line. So let's look at some examples here. So let's say if I want to find the equation of the line in each case, and I'm just going to give you different information. So the first example, let's say I have a slope of 1 and y-intercept of -4. And then actually, instead of having a slope of 1, let's do a slope of -5/3, since we often have slopes that are fractional, as we know. Another example, find the equation of the line that passes through the point 2, -3, and 5, 12. Okay? So you know 2 points the line passes through, and that's it. And convert, at the end, I would like you to convert the second one. So I want you to write it in slope-intercept, ultimately, and general form. Right, so slope-intercept form and general form. You might have to start with a different form, though. For the second example, my hint is you're probably not going to be able to write it in slope-intercept form right away, or general form right away. You're going to have to write it in one of the other ones and then convert to that. Okay? So, all right. So for those of you watching this online, Forgot to record it, but there's the solution to the first part. That was a fairly easy one. Let's go and look at the second one now. If I know the 2 points the line passes through, trying to find the equation line in slope-intercept form. What's the first piece of information that we need no matter what form of the equation we're using?
Slope.
I need to know the slope, yeah. So I'm going to have to go ahead and find my slope first. And what's the formula for that going to look like, Jake?
It'd be 12 minus negative 3 over 5 minus 2.
Absolutely. So we'll end up getting 15 over 3, which reduces to 5. So it's got a slope of 5. So we'll get, and so we have a slope of 5, and we have 2 points the line passes through. How many of those points do we need to actually write the equation line using point-slope form? Just 2, right? So either or, right? Well, you know what I'm going to do? I know this is a pain in the butt at the last second here, but I'm going to actually make this 1, negative 3, just to, I wanted to make sure that we are able to address a specific issue here. So I'm going to go ahead here and actually change this to 1, just because it's going to make it easier to sort of pick at a specific topic. So we'll make this 1, negative 3. I know that changes all your answers, so I apologize. So 5 minus 1 on the bottom there. Gotta really use the ghetto eraser here. All right, so 5 minus 1. Oh, gosh, I should do this. Gotta go and erase all this stuff. Hopefully I'll get better at this more. So we end up getting 15 over 4, which doesn't actually reduce. So just get rid of that there. And so we have a fractional slope, which is sort of my whole point here, because it's going to make things a little more difficult in terms of converting to general form, but it's definitely a skill we want to have. So in point slope form, does it matter which of these 2 points I use when I plug into point slope form to find the equation of this line? No, it doesn't, right? So why don't we just use the one with smaller numbers, because smaller numbers are always nicer, right? So we'll use 1, negative 3, which means my point slope form equation will be y minus negative 3 is equal to 15 over 4 times x minus 1, right? Now that's point slope form, but I also ask you to convert to slope intercept and general form, right? So that means right over here we have y plus 3, and we have this. So we want to distribute the 15/4 through there, right? And then we want to add the 3 to both sides. So we'll get y plus 3 is equal to 15/4 x minus 15/4, right? And then we got to go ahead and subtract that 3 from both sides. So we have fractional amounts. What is 3 in terms of fourths? How many fourths is 3? 12/4. So we have negative 15/4 minus 12/4. How many fourths is that going to give us?
27/4.
Yeah. So negative 15/4 x minus 27/4. So that's slope-intercept form, right? Obnoxious fractions, but that does happen sometimes. Now, if I want to put it into general form, or standard form, as it's sometimes called, which is ax plus by is equal to c, it's important that in the standard form that a, b, and c are all whole numbers, and that a in particular is positive. All right? So b and c can be negative, that's okay. But they need to be whole numbers, though. That's the thing. Or integers, I should say. Negative integers are okay. If I have this 15/4 and this 27/4, what's the good way to get rid of those fractions in this equation right here? And it's the strategy that we're always going to apply to fractional equations, whether we're talking about 2 variable or 1 variable equations. Yeah, multiply the whole thing by whatever and if this happened to be 4 and maybe a different number, you're going to multiply the whole thing by whatever the LCD, the least common multiple of these numbers happens to be. If you multiply the entire equation by that, it's always going to clear out your denominators. That'll come up on some examples in the homework tonight where you have fractional linear equations that you have to solve. In any case, we want to multiply. I'm going to rewrite this in the next page here, since I don't have any more room here. Y is equal to 15/4 x minus 27/4. The first thing we always want to do is to get rid of any fractions. Did not mean to do that. Get rid get rid of any fractions by multiplying by 4, and so we'll get 4y is equal to 15x minus 27. And the last thing I want to do is to get the ax plus by part going, which means the 4y we should subtract to put it over here, and the 27 we should add to put it over there. And if we do that, and then I'm going to put all the x and the y stuff on one side, so 4x or 15x minus 4y would go on this side, but once again, it doesn't matter with equations what side they go on, right? It's called the symmetric property for a reason. And so we'll get that equals 27. And so this would be my standard or general form of the equation. So being able to convert it into any form that I need is an important algebraic skill that will come up. The general form part is going to come up on, whoops. Once again, man. No, I'm not going to waste time erasing that. But this is going to come up when we get into solving systems of equations. And certainly knowing how to put it in slope-intercept form is important for graphing it. Although you can graph it when it's in point-slope form as well. All right, let's take a quick break. So it's also important that we talk just really briefly about parallel lines, lines that never intersect versus perpendicular lines, lines that intersect at a right angle, right? We know if two lines are parallel, what is true about their slopes? Same slopes. And if two lines are perpendicular, they have opposite reciprocal, right? So opposite and reciprocal. I can't get it in there. You get the idea. And so if the slope of the one line is m, the slope of the perpendicular line would be negative 1 over m, right? Opposite and reciprocal. All right, so if I asked you, find the equation of the line that is, sorry, just couldn't stand to look at that D. Find the equation of the line perpendicular to the line defined by the equation 3x minus 2y equals 7 with an x-intercept of 2. Okay. Find me the equation of a line, and this can just be in slope-intercept, that's fine, but find the equation of the line perpendicular to that line with an x-intercept of 2. And then ultimately write it in, you can start off in any form, but write it ultimately in slope-intercept. Don't worry about you don't have to worry about standard form this time, but write it in slope-intercept for me. Good catch. So we're trying to find the line perpendicular to this one with an x-intercept of 2. To know what slope the line that we want has, we first need to know the slope of this line, right? And what's the trick to that? Put it in slope-intercept form, exactly. So we'll go ahead and get the 2y by itself on one side. So we'll get 2y is equal to, I'm going to add the 2y to both sides and subtract the 7. And then go ahead and divide off the 2. And so that means my slope of that line is 3/2, right? Because it's in slope-intercept form. What's the slope of the line perpendicular to that? Negative 2/3, yes. So that's the slope of the line we want. And our line has an x-intercept of 2. What point does that mean that it passes through? 2, 0, yep. So we have a point, we have the slope. Let's use point slope. Y minus 0 is equal to negative 2/3 times x minus 2, right? And so we'll get y is equal to negative 2/3 x plus 4/3 when we distribute it to put it into slope-intercept form. So negative 2/3 x plus 4/3. All right, so that's how we can use the idea of perpendicularity to find the equation of a line if we know another line that it happens to be perpendicular to. Okay, last basic concept we're going to cover today, just as review once again, is basic linear, single variable linear equation solving. Let me write that down. Oops. About solving fractional, That's the tricky part. Is the regular ones you're probably pros at by now, but we're solving fractional linear equations. So, for instance, if I have 5x minus 2 divided by 2 plus x plus 1 over 5 equals 3 over 10. So this is a very fractional equation. Thankfully, in this case, all the denominators are nice whole numbers. Turns out that wasn't the case. That would be a little more difficult. But it is a fractional equation. And there are two ways of dealing with it. One of which would be to take this whole side right here and combine it into a single fraction by finding the LCD and then convert it to the LCD and add them together. But that can be pretty time consuming. The method that I prefer in all cases, anytime I have any type of fractional equation, is to do exactly what we've done so far with the simpler fractional equations, which we've seen, which is what? What did we do when we had like the 2 in the denominator of those midpoint ones?
You multiply by least common multiple.
Yeah, I multiplied the whole thing by what the LCD of all the denominators was, which it was 2 because there's only one denominator in that case. But now we have 3 denominators. One's 2, one's 5, and one's 10. So what could I multiply the entire equation by here to clear out my denominators? What's the LCD? 10, yep. So what I'm going to do is I'm going to go through term by term and figure out how this is going to reduce. So if I multiply 10 by this first term here, 5x minus 2 over 2, if I multiply 10 by this, right, 10 will be divided by 2, and then I can distribute it through here. That's the way we're going to look at this. We're going to try and multiply the 10 by the 1/2, and then whatever's left over when I reduce 10 times 1/2 has to go ahead and multiply whatever's on top here. And I'm going to do that in 2 steps. So what's 10 divided by 2? 5. So 10 divided by 2 is 5, and then that has to then be distributed to the 5x minus 2. So I usually like to write this in 2 steps. I don't distribute right away just so I know what I'm doing. Now, when I multiply 10 by x plus 1 over 5, I'm going to divide the 10 by the 5 first, which will give me what? 2. And then that has to be multiplied by x plus 1, right? So the whole point is, in both cases here, 10 divided by 2 is evenly divided into 5. 10 divided by 5 is divisible evenly by 5. It becomes 2. Whoops. Right. And then lastly, 3/10 times 10, of course, is just 3. Right. So we have all our fractional. We could essentially think of, this divided by 2 as a coefficient in front of the 5x minus 2 of 1/2. Right. So think of it as just 1/2 times 5x minus 2, and 1/5 times x plus 1. And by multiplying 1/2 by 10 and 1/5 by 10, we've made them both whole numbers now. Right. So instead of being fractional coefficients, they are whole number coefficients. And this is also whole numbers. And so there's no fractions left, which is very nice because we know that dealing with fractions is always more time consuming and tedious than dealing with whole numbers. So we're going to proceed by simplifying both of these expressions here to get 25x, minus 10, and then 2x plus 2. And then we'll go ahead and add these together. So 25 plus 2 is 27x. And I'll go ahead and subtract the 2 and add the 10. So 3 minus 2 is 1. And plus 10 is 11. So x should end up being 11 over 27. So, solving linear equations, specifically ones that involve fractions. Okay? All right, so that's going to be it for that covers all the topics that will be on the homework. That will, once again, the homework tonight is from the worksheet that I handed out in class today, which I will also email out to everyone in PDF form, particularly for the people who aren't here. And the exercises I would like you to attempt are, and this will also be in the email, handouts. I'd like you to do numbers. Please do numbers 3 through 6 all. 14 16, 18, 19, 20. I probably could have just done 18 through 20 all. It's okay. 23, 25, 26, 27 through 32 all. And then just 36, 38, and 39. A lot of these are pretty quick. I think you're going to blaze right through them. So 3 through 6 all, 14, 16, 18, 19, 20, 23, 25, 26, 27 to 32 all, 36, 38, and 39. And that will cover all the different topics that we talked about today. Tomorrow we'll mostly finish up our Algebra 2 review, talking about a lot of inequalities, quadratic functions and equations, solving them, as well as quadratic inequalities. Okay?